Welcome to a lesson with Dr. Pal. We're going to discuss and derive a result about ramification indices and inertial degrees of a prime um, in a ring of integers, OK, of a number field K. Okay, let's begin right here looking at a homomorphism between two simple OK modules. Now, this is simple because P is maximal, and this is a field, meaning that the only OK submodules here are trivial ones, either the whole thing or the zero of this guy, which is represented by the prime P, what we're modding out by. Now over here, because OK is a Dedekind domain and has unique factorization of, and hence has unique factorization of ideals into primes, if you have anything between these guys, it's either going to be down at the bottom or at the top. So if we were to establish a homomorphism between these, it'd be pretty clear how to make sure it's an isomorphism. Because the kernel over here to back here can only be, there's only two options, and the image over here is only two options. If we can just establish that something, after we have a well-defined homomorphism, that something non-trivial over here is sent to something non-trivial over here, we'll have an isomorphism. So what if we just define our map here by a multiplication by an element that lives in here but not in there, like this? Then if this were to work, then if we have like the representative of 1 over here, which doesn't live in P because otherwise P wouldn't be a prime ideal, it wouldn't be maximal, it would be all of OK, then the image of 1 is actually just A itself, which by definition does not live in here but lives in here, so it's non-trivial, therefore an isomorphism. Now, is this map a homomorphism? Is it well defined? Well, take the zero of over here, or any representative of it, so anything that lives in this ideal, P, and we take it and multiply it by A, which lives in Pn, and we're actually going to get something that lives in we're going to get something that lives in Pn plus 1 because x lived in P, so the product will be live in here, which is exactly what we wanted. So the zero of this guy over here is completely sent to the zero of this guy over here, which makes this as a well-defined homomorphism. So we have a nice isomorphism, which means that, now remember, that the index of P and OK is finite. And so this finite index is going to be the same as this finite index. Okay. Now, and since this is finite, and it's a field, we know it's a finite field. What's its characteristic? Well, take any prime P that lives in Z, that this lies over. So let's suppose that, so this prime ideal lies over a prime ideal PZ, and we mod out by that P, and what we get is this will be a field of that characteristic P, and any finite field of characteristic P has size P to the F for some F, and we'll just say that F right here, just say that's the inertial degree of this prime lying over this prime. Okay, so this P lives in OK, and this little p lives in Z, which is actually the ring of integers of Q. So in that extension there, so this the inertial degree is F, and it just has to do with, in this particular case, the sides of this finite field. And or as a field extension over as a field extension over the prime subfield, just Z over PZ. Okay, so the degree of that. All right. Okay. So let's take a look at P thought of as an OK and as a principal ideal generated by P, we can decompose it into a product of primes. Okay, so product of primes we've decomposed it into. And by the Chinese remainder theorem, if we mod out by P and OK, that's going to be equal to this direct product right here. And we know something about this index P in there. We know, for instance, that OK is isomorphic to Zn via a Z module homomorphism. And in particular, you could think of it this way, and P is in Z. So this works. We could think of, okay, it's just the index of PZn and Zn. And what is that index? It's just P to the n, because this right here is isomorphic to just n copies of ZPZ in a direct product. So we end up getting that P to the n is this index, and we're going to use that idea as we look over here and analyze what's going on this side over here. In particular, we know that if we find the index of this in here and the index of that in there and so forth, that if you just simply multiply all those indices together, you should get P to the n over here on this side. Okay, and that's via the Chinese remainder theorem. Okay, so let's look at that now. Now, if we think about this, let's look at this right here, this index, OK, and P1 to the E1 living in OK. Now, we can look at the various ideals here, like P to the 1, E1, it lives in P to the 1, E1 minus 1, and so forth in a chain all the way up to P1, and that's an OK. Now, we showed that actually the index of this and this is the exact same as the index in this and this. They're all the exact same, and that was the first slide that we had. So using that idea that all those are the exact same, and we can say we can use F1 as for the inertial degree of P1 lying over the rational prime P, or a little p here. Okay, so that would be PF1. And how many of these do we have? We have E1 of them. So looks like this index is simply P to the E1 F1, and all the way down the line. And if we're looking at relating powers of primes, remembering that on this side, this is P to the n, and it's equal to the product of these things. If we just look at the exponents and add them together and equate them here, we end up getting this relationship right here. So that the product of these E1s and these guys, so let's call these E's a name. Let's say it's the ramification index of that of one prime lying over another one. So the prime that it was lying over was a rational prime in Z, and we'll call these ramification indices. And they came from the unique prime factorization of the principal ideal P, OK, into a product of prime powers. Okay. Now so that's that one subcase, all right, of this idea. Now let's kind of beef it up a little bit. So we were looking at an extension. We were considering the extension like K over Q. But what if now we kind of go a little bit further and look at an extension like L over K, and look there. So maybe we have primes in OL, and maybe those primes lie over prime in OK. So a prime in OK, and then it extends to primes that lie over it in OL, just like what we were just doing is we were looking at primes in in Z and seeing how and looking at primes that were over them in OK. So let's look at this extension L over K, and let's suppose now, so we're going to let N be something else now, all right? So before, I just kind of threw N out of, seemed like out of the blue, where did it come from? I just knew that right here, this was isomorphic to Zn, where N was the rank here. Now, how did I get that Zn? N is actually the, if I thought about K as being a field, and this field extension, a field extension here, K over Q, N was actually the degree of that field extension, or the dimension of K as a Q vector space. So that's where I was getting the N there. Now over here, the N that I have right here is going to be the degree of this extension, so L over K, is thinking of L as a K vector space now, if you will, and looking at that dimension. Okay, so you know that OL is and if you look at the ring of integers, OL, which contains OK, it's a free OK module of rank N. Similarly, as we were thinking of OK as being a free module of Z, but we're using the same variable name, but you can think of them as being different. So here we're looking at this case now with extension L over K. Okay. So we can think about the index of a prime of OL in OL right here. Okay, so prime, actually, no, this prime right here lives in OK. So now, okay, we're going to take a prime in OK, all right? And just like we took a prime in Z, but now instead we're going to take a prime in OK, and then take this prime, multiply it by OL itself, and look at what it is like in OL. Just like we were thinking about, you know how we got that P to the N before? We're going to do the same thing here, but we're going to call it a P to the M right now. So we know that OK over P OK to the okay, so right, because it's a free OK module, and so we can think of this as so we know that OL is like OK to the N, and so in that sense we can get an isomorphism over here, which tells us that we're going to get, okay, so then if we assume that the index of P itself in OK, which is a finite guy, which we know is a power of P from before, so this would be like the P to the F thing that we had before, but instead here we'll just call it P to the M, and so this is equal to P to the M. So it looks like overall this index is actually going to be P to the M times N, because each of these guys is P to the M, and then we're going to have a multiplication by N. So we're going to have a P to the Mn. Okay. Now, this ideal, and properly we should think of it this way, multiplied by OL, has, so lifted up into OL, has a prime factorization. And we can look at the index of, if we want to look at the index of this in OL, now we just discovered that that index was PNM, right? That index in OL is PNM. And this guy right here, so the index by the Chinese remainder theorem, we can do the same type of thing with looking at indices like of this in OL times that in OL times that in OL and so forth. Let's take a look at this one right here, OL and P1 to E1, okay? And let's consider what's going on with this. Now, this index, using the same idea that we had before of that homomorphism or isomorphism between simple and OK modules, but in this case it'll be OL modules. we can actually see that this will be just equal to this raised to the e to the first power, using the same idea as we had before. And this guy right here, let's think about what this is. It's actually going to be, okay, if we define, let's define what we mean by f1. F1 will simply be the dimension of this as an OK over P vector space. Okay, so dimension of that. Okay, so that's what F1 is going to be. Okay, so if this is as a vector space over this as thought of as a field, but then if you think about it, okay, this thought of as a field, okay, P, now these are all done by indices, which is kind of interesting. Notice how it's a P to the m-1 because indices are different than dimension. It's like you're counting like cosets. Like for instance, the cosets of 0 and z, pz is actually just p. Over here, the cosets of the prime subfield in the full thing is actually, so you look at, you're just kind of crossing out one of your components and you're looking at how many things you have in the other components. So p to the m-1. So p to the m-1 times p is actually p to the m, which we said was the size of OKP to begin with. So we can actually get the size of OKP that way. And then similarly, you look at this over here and you can do something similar, just crossing out one of the components in each component in this as an OKP vector space. That cutout was p to the m you're cutting out. But nonetheless, what we have is you have the size of this we're going to label as p to the m times f1, where we'll just say f1 is the inertial degree of this funny looking p over that script p. So so kind of an inertial degree in that sense. And m comes in from where we were already. So instead of just using p to the first, we have p to the m now. And then the E1 comes from that power, which came from this description right here. So we end up getting a very similar thing. So p to the nm is equal to this product, and taking the m out from both sides or factoring out, we end up getting the same idea. So where n is the degree of the field extension, and that's equal to the sum of these products between inertial degrees, and the I wrote index, but inertial degree and the ramification index as we go along there in that particular case. All right, and I was just reminding us what that inertial degree was, simply a dimension of this field extension, or the degree of this field extension, which is the same as the dimension of this as a vector space over that. Okay. And all right, let's look at the case though, because something happens when this field extension is normal, meaning that all the endomorphisms, the endomorphisms of L into the complex numbers that fix K actually remain within L, so you actually get a group out of them, a Galois group. In particular, so if you take any of those endomorphisms, which are now automorphisms of L, and you apply them to any of these prime ideals, you're going to get something that these prime ideals, you're actually going to stay in OL. We're going to get something that's still integral. In fact, these guys right here, I mean, you'll still be in root of a monic polynomial with coefficients where they where they should be in Z and so forth because of fixing things and all of that. So we end up getting ideals or still stay ideals in OL. Okay, so we get actually that the Galois group acts transitively on these primes, so we can actually go back and forth between all these primes given certain elements of the Galois group. If it's not transitive, then we can pick a prime that's not in the orbit of maybe say the first guy right here. Okay, so and let's see. So what we're going to do is we're going to take that guy that's not in the orbit, all right, and we can choose with the Chinese remainder theorem, we can choose an element x, which is congruent to 1 mod all these different primes, these in the orbit of this guy, and we can also choose something that's congruent to 0 mod this prime. All right, so let's see what this means. Since mod 0 here, that means that x is going to be contained in there. In particular, its norm as we go from L down to K, which is going to be a product of all the automorphisms applied to x. It's going to live in this prime. Let's see, it's going to live in this prime P, and that's because this product actually is going to be contained in this prime. And since this product actually lies in OK, and we know that, so anything that's in here, that's in OK, the intersection of this guy with OK is actually P. So you know that X lies in this script P right here. Now, what about up here? What does this mean? This means that X is not in here, and in particular, okay, and especially if sigma is just the identity automorphisms, in particular, that means that the inverse of, so sigma inverse of X is not in here for all sigma. All right, so you know that much so far. So now we know that the norm of X from L down to K is cannot be contained in there. Now, why can't it be contained in there? That's because right here, you can express the norm as products of sigma inverse, and all these guys don't live in there. Since none of those guys live in there, then that means, and it's you're looking at a product of it, and this guy's prime, that means none of them could have lived in it. Okay. So, or it means that, which in particular means that, okay, so this is the product, right? So you have a product of guys, and each of those guys don't live in here. So that means their product can't live in there, because if their product lived in there, that one of them would have lived in there because of that's prime. Okay, so you know the norm doesn't live in here, but you also know that this norm is the norm of X. As we were looking at it, we actually saw that from this side that it lives in the prime P. Okay, so it lives in here, but you also know that this is contained in here since this lies over P because it was in that factorization. Ooh, which is a contradiction. All right, so that's a contradiction here. What does that mean? That means that the Galois group acts transitively. So since the Galois group acts transitively on those on these primes, we actually get we actually get a nice isomorphism between the quotients when we quotient these guys out. And in particular, we'll actually find that the ramification indices and the inertial degrees are actually the same all around for each one of these guys, just because the Galois group was transitive. So we actually get that this is true and this is true. And so our sum actually reduces to just simply saying maybe R times E times F. Like there's an established E and established F for any prime that lies over another prime here in this extension. This happens for Galois extensions. Thanks for watching.